Right, thanks for joining me with some exam question walkthroughs. And I thought what I'll do in this video is look at some titration questions that involve citric acid. A lot of the times when you see them in textbooks, they give you a strong acid, strong base with a beautiful equivalence point pH of around 7, and they're fairly straightforward. The ratio is 1 to 1 in those reactions. But this time, when you chuck citric acid in there, it tends to confuse a few students. So let's do citric acid and sodium hydroxide titration question, and that is a strong base, weak acid. So let's go through and have a look at some questions. I'm going to do 2 of them. All right, the first one here says, as it asks you to draw the structure of citric acid. It says a sodium hydroxide solution was titrated against citric acid, which is triprotic. And then they ask you to draw it. Now, they do give you the IUPAC systematic name here, which makes it a lot easier if you know how to understand it. And so if we look at here, it says propane, so there's 3 carbon parent chain. Then it says 2 hydroxy, so that means on the second carbon we put a hydroxide group. And then 1, 2, 3 tricarboxylic acid, so it's saying we need a carboxylic acid group of each of these carbons. Now I'm going to draw it here with the groups, but keep in mind this is not how it would actually exist in real life, because of course you have to take in the stereochemistry and the structure and shape of the molecule. I'm just going to be drawing it here as to emphasize the groups. So we have a carboxylic acid group on the first carbon, we then have one on the second carbon, and then we have one on the third carbon. And then of course we fill in our hydrogens. So that is citric acid there, and it's triprotic because of these 3 carboxylic organic acid groups, and they can ionize in solution to donate 3 H pluses. So for 1 molecule of citric acid, it can liberate 3 H plus ions, or they can donate them to solution. Now in this question here, it says, how could a computer-based technology be used to identify the equivalence point of a titration? Well, normally with the equivalence point, remember we do that with indicators. The equivalence point is the point in the titration where the reactants are present in the solution according to the reaction ratios. So if you're taking the simple titration example of HCl and sodium hydroxide, there's 1 mole of each of those in there. So the equivalence point is when you have 1 mole of HCl and 1 mole of sodium hydroxide. In this case here, it's citric acid, and so we're going to be having a 1 to 3 ratio. So the equivalence point is just that point in the titration where the concentrations of the reactants are the same as what you would see in the balanced chemical equation. And of course what we want to do with all titrations is stop the titration there. Okay, and that's when we use an indicator to change color close as possible to that equivalence point. And we want to choose one that has an indicator endpoint, that is the point at which the indicator changes color, close to the equivalence point as possible. And so a popular one is phenolphthalein, going from colorless to pink at around 8.3. So here it's saying a computer-based technology, not a indicator solution. So in answering this question here, first of all you want to say what the equivalence point is, and then you want to say that you have a computer-based technology such as a data logger or a pH probe that will measure the pH at that point. So that's what you want to say in that section there. Let's turn it over to the actual equation for calculations and see how we go here. So let's read it off. The sodium hydroxide solution was titrated against 25 ml samples of 0.1 citric acid. So let's write the equation. So we've got citric acid here plus 3 sodium hydroxide to give you the salt and water. Okay, so remember, if we turn this over, you can see that we've got citric acid here. So when these protonate to solution, there's 3 places there that the sodium ion can combine with. So for 1 molecule, you have 3 Na plus ions associating with that molecule, and so that's why I've got the 3 there. And remember, the hydrogens go down by 3 because they have been lost to solution. All right, so that's our equation. So the next thing is what we want to do is we want to put down the information. So it says 25 ml samples of 0.1 molar citric acid. All right, so let's put that down. 0.10 molar, and we have 0.025 litres. It says the average volume of sodium hydroxide used was 41.5, so let's put that down. 0.0415 litres, and we don't know the molarity. So here's the characteristic thing with titration questions, is that we know this here, so we can calculate the number of moles of acid added, which then will allow us to calculate the number of moles of base present. Once we know the number of moles, of course, we can use that with the volume to work out its concentration. So let's do the calculations, right? So the formula is C equals N over V. So the number of moles is equal to concentration times volume. The concentration that we had was 0.1 and the volume was 0.025. So when we times those together, we get 0.0025 moles. So that's how many moles of acid are present, and they reacted with 3 times the amount of sodium hydroxide. So we go a mole of OH present is 3 times 0.0025 equals 0.0075 moles. So that's how many moles of hydroxide are present. So now, of course, we can use that same formula as we did before to work out the concentration of our sodium hydroxide. Divide that by the volume average volume that we got for the titration. Whoops, that's 0.0415 litres, and that turns out to be 0.18072, and we round that to 4 significant figures, and we get 0.181. So hopefully that makes sense to you. It's pretty straightforward with all titrations. They can complicate a little bit more sometimes by adding a dilution in the first step to dilute the sample down. It just means that when you get to here, you have to then work out and take into consideration that dilution factor. Okay, let's do another question. All right, here's another question, and this one here is a little bit different. So let's check it out and see how we go here. Let's read through the question. It says, a chemist analyzed aspirin tablets for quality control. The initial step of the analysis was the standardization of sodium hydroxide solution. So here we're going to do a bit of a revision now. Remember that sodium hydroxide solution is not a very good primary standard. Remember, the features of a great primary standard is that it has high purity, has a high molecular mass, so that minimizes weighing out errors. It has a known chemical formula. It does not react with anything in the air, so it doesn't absorb water, and it doesn't absorb CO2, and it's stable once it's made up. It doesn't decompose or break apart. So sodium hydroxide, unfortunately, does react with CO2 in the air, and it absorbs a little bit of water as well, even though you're making up in solution, but it does absorb the CO2. So that's going to change its purity and therefore the calculations involved when it comes to with its mass. So what we need to do is we need to standardize that sodium hydroxide solution so we know exactly its concentration. And they're doing it here with a sample of standardized HCl. So let's have a look at the question. Standardized HCl. Because remember, HCl is not a very good primary standard either. But here we've got it's already been standardized. So we're going to use that, which is the secondary standard, to standardize our primary standard here, sodium hydroxide, the one we're going to be using in the titration. Right, so let's have a look at the details. And so it says 3 samples, 25 ml samples of 0.1034 HCl were titrated with the sodium hydroxide solution that you're trying to standardize, and they tell you the average volume. So let's write a equation. So sodium hydroxide plus HCl gives us sodium chloride plus water. So it's a neutralization reaction like all titration equations processes. So let's write in the data here. Our sodium hydroxide is the volume anyway, was our average so 0.02575 litres. We don't know the molarity. The HCl, we were using samples of 25 mils, so let's put that in, and we know the molarity, 0.1043. So just like in previous question, we can see that we've got two knowns here, so that allows us to calculate the number of moles. Then once we know the number of moles, we then go across and work out the number of moles of OH present, and then we work out its concentration. So let's do that right now. So the moles is equal to concentration times volume. Concentration 0.1034 times the volume 0.025, and that works out to be 0.002585. So the ratio is 1 to 1, so that means, of course, that that's the same number of moles of OH minus present. And so therefore the concentration of OH minus, or the sodium hydroxide, is the number of moles divided by the volume. That's 0.002585 divided by the volume, and we know the volume here, 0.02575, and that's 0.1004 moles. Okay, so that's the concentration of our of the sodium hydroxide solution. So now let's see what the rest of the question says. All right, so we've standardized our sodium hydroxide. Now, of course, we have to analyze the aspirin, which is an acid, in the tablets. Right, so here we go. 3 flasks were prepared, each containing 25 mils of water and 10 mils of ethanol. An aspirin tablet was dissolved in each flask. The aspirin in each solution was titrated with the standardized sodium hydroxide, and we got the equation. So they give you an equation. So we know for our sodium hydroxide its molarity, so let's write that in, 0.1004. We just calculated that. Here is the average titration, so you can see we've got 3 different values here. They're pretty close to each other, so we can all use all 3. If they varied significantly, you would ignore the most outlier volume there, but they're all pretty close. So if we take an average of that, we get 16.55 mils, and of course we convert that to litres, and that's our volume that we can use there, right? We know that we used 25 mils dissolving into the tablet, so 0.025 litres. Now, here's the difference between this question and the previous question. The previous question that we did asks for the concentration of the unknown solution of the citric acid, I think it was. Here we're not asking for a concentration, we're asking for the average mass of aspirin in the tablet. So it's the same process we go through initially anyway. We find out the number of moles, the number of moles of our sodium hydroxide. That tells us the number of moles of our citric acid present. But instead of going to a final answer of molarity, we want to go to a final answer of grams. So let's do that. So the moles of the sodium hydroxide used is the concentration times the volume. The concentration was 0.1004, and the average volume that you use is there, 0.01655. That means that how many moles of OH was used in the titration was that. Since it's a 1-to-1 ratio, the number of moles of citric acid is the same. Now, we want the final answer in grams. So remember we had a relationship before, is that moles is equal to mass divided by molecular mass. Well, we know the moles, we want to calculate the mass, and of course we can do the molecular mass. So let's put that into the equation and see how we go. All right, so we have the mass is equal to the number of moles times the molecular mass. The moles is 0.00166. The molecular mass is 180.154. Now I've got the data here already calculated, but in exams it's good to show you how you got that. So you would put a bracket there and you would actually calculate the molecular mass out and show the examiners that you know how you got that value there. And then of course you get the answer 0.2993 grams. But the question says milligrams. So we need to express it as milligrams. So milligrams is times by 1,000 and you get 299.3 milligrams per tablet. Okay, because remember they got tablets and put each tablet into separate beakers. Now the last bit of the question here, it says, why was it necessary to include the ethanol in the mixture? Well, this is a bit of a tricky question for, I guess, HSC students, in the sense that you're not expected to know the structure of aspirin. However, you can imply the structure based on the fact that you have to add ethanol to the mixture. So it is there to help it dissolve. Ethanol is a compound that has a benzene ring in it, and a benzene ring is hydrophobic. In other words, it's non-polar, and so therefore we have the polar group where we have the carboxylic acid, that's polar, but the large majority of it is non-polar hydrocarbon, and therefore we need, in order to dissolve it, a substance or a solvent that can dissolve both polar and non-polar, and we know that ethanol can do that. So here in this one line you would just say adding ethanol increases the solubility of the aspirin into the solution so that all the aspirin can react with the sodium hydroxide. Okay, because there's no point in doing a titration and trying to find out how much aspirin's present if not all of it dissolves in solution so that it can react with the sodium hydroxide. So that's what they're expecting you to say for that 1 mark there. All right, I hope that makes sense, those 2 questions on citric acid. I'm going to make quite a few more videos in this style to walk you through exam questions. And as we do it, we're going to not only do the answers, but we're going to use that as springboards to do some revision on some content. All right, see you in the next video. Keep doing chemistry.